So in a previous video, I went over the math of how to design this battery charger. In this episode, I'm going to do the actual build. But for those of you who weren't interested in watching the math video, here is a quick recap of what is going on. I chose this Maxim integrated DS2715 charge controller to build a 9-volt battery charger, which is funny because it's a charge controller designed for many amps of current. But this is the basic application circuit for the kind of charger that we're building. And the long and short of it is we got the battery pack here, we got a thermal detection here, an NTC thermistor with a 10K to balance it out. VBAT detects that there's batteries. We set the voltage divider here based on how many cells, so that VBAT sees the voltage of one cell. We set the current sense resistor down here to maintain a voltage drop of 121 millivolts. And to maintain that, the charge controller will control this P-channel MOSFET right here, linearly regulating how much juice can flow through. VCH output is negative only, which means we need this pull-up resistor to tell the MOSFET to turn off when VCH is doing nothing. This is a trickle charge circuit for like when the circuit's not actually running. We omit that. The design of this guy is based on the fact that we have a fixed battery pack and a load. So that load is whatever the device we're running. We don't need that, which has certain things shift around, like the timing circuit, which is normally a little MOSFET that grounds out this resistor. That resistor sets our charge time, so that when you plug in power here, it fires that resistor, pulls that to ground, sets our charge time. My version of the schematic is here. There's our pack. The NTC stays the same. The voltage divider, we're using 750 and 124. MOSFET stays the same. 1.2K here to set the bias of that MOSFET, because VCH needs to make sure that it doesn't sink any more than 20 milliamps of current. 10 milliamps is target. Our Schottky diode is moved here so that the power from the battery cannot backflow and power this circuit, because we don't need this circuit powered if there's no power. Our LED bias for 12 volts via 2.2K to get our 70 milliamp charge, accounting for 10 milliamps of losses, a 1.5 ohm resistor, and our timing circuit, instead of that MOSFET, gets a Schmidt channel inverter. Our timing is set from 91 to 100K, as explained in the math, to give us the roughly 2.3 to 2.5 hour charge we want for this battery at 70 milliamps. And of course, this 74HC1G14, which is one of these little cuties right here, it doesn't like running off 12 volts. So we have a 10K resistor, arbitrary, because that little guy only needs microamps to run, and then a 5.1 Zener diode to make sure this gets the appropriate amount of juice that it likes. So, building on it, what do we have for that? We got ourselves a perf board, a 5x7, which I'm going to install in some form of Hammond enclosure. It's going to match the effects pedals. I found this PC mount battery terminal. That's going to be soldered right onto the board. So the idea is there's going to be a hole in this guy, and then when we're ready to charge, we just kind of stick the battery through the hole, snap it on, and off it's going to go. We have our charge controller on an SOIC16 adapter. For the MOSFET, you gotta choose a MOSFET that's going to be able to handle the current you're running. And not only does it have to be able to handle the current you're running, it has to handle more than the current you're running, because it's running in linear mode, so it's going to be burning up power. It's going to start to get hot. In our case, 70 milliamps, 80 milliamps, we don't need a whole heck of a lot of MOSFET. I'm using this little cutie right here. That's an IFRD 9010 and a PDIP 4. It's rated for about 1.1 amps, and in testing it had no problem working with this circuit. And then the rest of it, well, pretty much just a bunch of resistors and capacitors, and here is the PCB layout that I've come up with. We got a random floating little representation of an MLCC, because I'm probably going to add a capacitor across the terminals of this guy just to stabilize things a bit. So this layout, we got positive power coming in here. There's our 47U reservoir. There's our negative power coming in. First thing we have is 2 LEDs, not one. You know, I don't know if you're like me, but you have a tendency, little friggin' wall wart powered devices, if they don't have some sort of light that tells you that you left them plugged in, you forget them plugged in. So So this LED is just connected right to the power input to say, hey bud, you left this plugged in. This is the actual indicator LED, 2.2K to LED pin, and on the positive bus on this side. The positive flows this way. There's the 100Z for the VDD input and its little buddy, the 0.1U. Then positive also goes this way. There's our Schottky diode, an SB160, and then that goes to the 4.7U and the MOSFET with the 1.2K pull-up resistor. And then the gate goes all the way over here to VCH, and then that goes out to the battery terminal. You're going to notice it's the square one on the 9-volt battery. The circle one is positive, which means on the board, the square one has to be the positive. Then there's our 750 and our 124 voltage divider going to VBAT. And then here, this trace goes all the way around there, bud, to the 1 meg, which goes to our Schmitt inverter. Off the plus, there's our 5.1 Zener. There's our 10K. But then on the other side of the circuit, going all around here is the main negative bus. And it goes to the current sense resistor with a trace going to the sense pin. They want you to use something called the Kelvin layout. So basically there's an individual set of traces coming right off the resistor to the sense pins. You don't use the same trace. It would have been so convenient to say run the ground coming off the sense resistor up this way to the VSS pins instead of going overland right here. But no, we need to use an individual trace. Here becomes our post sense ground bus. You can kind of see it star connecting right down here. One line goes up to the other half of the voltage divider. Another line goes down to the battery. Another line goes here to the NTC, which then goes up to the thermal pin. And then there's our 10K that connects it to the div pin. And then another line goes this way to the negative of the Schmitt channel. Schmitt channel? It's okay. And then it passes through one overland connection to the mode, to connect to ground, to connect to ground. There's 2 connect to ground pins. They don't really explain what they do. They just say connect those to grounds. And the 1 and 2 VSS pins don't explain why there's 2 VSS pins. I wouldn't be surprised if this VSS pin's connected to, that's the ground source for VCH. And then we have a 0.1U going over to our C bias. Apparently that has something to do with an internal regulator. They probably explain a little bit more what some of these functions do, but once I got the gist, I was done. Oh, so where do we start with this buddy here? Well, for starters, we no longer need the pins on this adapter board. So we're pulling them. Gonna have to also make sure that we clear them out. Now, if you're starting from scratch, this is obviously not a part of the process. Okay, now that guy's ready to go. So one part of the process is getting your ICs mounted. Usually this is a little bit easier if you can pin it first, but in this case, we don't want pins. So we're starting from scratch with a bare BOB00717 adapter for the SOT23 package, because that's what I'm going to be using. I'm going to be using little 74HC1G14 Schmitt inverters, single channel. They're SOT23-5. This is a -6 adapter, but that's fine. You know, be careful when you're ordering these guys. They all look the same. We start off by schmooing down some Rossmann glue here. This is a Chip Quick NC919 Tacky Flux. Not in focus. Take my word for it. I just use my regular leaded solder. Get that blobbed over. Hey! Okay, it's right here. It's easier to identify these guys because pin 1 is on the side with 3 legs. It is hard to flip them over, and they always turtle on you. If you look carefully, you will see the slightest little dot in the corner. Clean that tip, and then boop. Then on this side, boop, boop, boop. Haha. And to clean that, alcohol on a toothbrush. Give it to brushing, paper towel. And she's clean enough. All right, this guy here. You know, you kind of want to mount that socket down, but it's like, you gotta start figuring where we want our components to go. I'm gonna start off by drilling the holes. I have these represented here to represent the kept nuts that you use. And they are right here. 964 should give us the hole we need. This is not the same toothbrush, but I keep one handy. We're speccing this up for 9 or 632 mounts. So, you know, when it's all said and done, boom. Our NTC thermistor is going to live right about here. And I want to get it as high as possible. It's going to be in the general vicinity of the battery. So like as long as it gets to the battery as close as possible, it's going to be able to roughly detect the temperature of it. I want to set its height here. Look at the battery holder out of the way. We don't want it to touch the enclosure. That should be good right there. little whiff of solder to hold it into place. Imagine for a second we have a battery in here. Yeah, that's gonna be that's good. Oh, that's actually, it's touching the battery there, so that's gonna be good. Check our height. Yes, it will just clear the enclosure. Don't know why I started there. You're never sure where to start with these guys, right? But this gives us perspective. So sometimes what I'll do is just like lightly, I don't want too much solder or else it's gonna interfere with geometry on the other side, but if we just lightly tack them into place. Now, the SOIC adapter has a situation that you have to be mindful of, because on the reverse side is positions for a TSSOP16, and those are exposed electrical contacts, and this is a double-sided board, so if we don't insulate that as soon as we put this down, it's going to short out against any pathways running underneath of it. A traditional way of doing that is with some Kapton tape. Obviously, you need supplies to do this, like a bit of Kapton tape. Most expensive being is my 24 gauge tinned wire that I used to make the perf board connections. This was like 60-70 bucks for this roll, but it's 100 feet, so it's an investment, right? All right, now this guy's ready to mount. So it's great because now that we have a couple components in, we have enough perspective to maybe get this pupper plopped down. And we can quickly index it into place, because one of the reasons why I make it holes, because the leads and the components themselves are going to be how I batten down these hatches, like putting the C-bias capacitor in here like that. So for an example, with the 10K div resistor, we're going to take that lead, we're going to wrap it right back down and around, push it up through the hole. And we're going to grab onto it and pull until it threads like sewing. We're just going to chuck arbitrarily another resistor or something in here through some pins so that everything aligns, and we'll secure this div line in place. Nothing else connects there. Boom, I would just officiate it. There's a good chance we can go ahead and hook up this NTC. I use a little pin tool like this to kind of poke in a hole and make bend points. If we're lucky, we could fit 2 leads in the same hole if one of the leads is small enough. Should be able to. Ta-da! Gotta make sure our component's clear, like that's just. Any longer and we have a problem. It starts to get hairy underneath if you mount a lot of components. We're doing a weave here, or at least trying to. I'm gonna start by weaving this down through here and up through the hole right there, because we have an overland connection that we might as well go directly to mode here. Then connect to ground. That should be good enough, and this should secure all our ground buses. Pull our taut, solder it down, solder it to the IC. Now grab this weave, pull that taut, make sure it's good on this side, secure it. Pull our taut again here, solder it up, secure it on this side. Now we have to form it. It has to go over one towards the outside this way, then down, then turn again, to make sure geometry clears all the adjacent holes. Secure it down, flip it over, where you see, that guy goes right about there. We'll just stick a random whatever over here to hold it into position. A little tacky, just a slight bit, because this guy is gonna go down through that next hole once we determine our next plan of attack. This is going to interface with this NTC. I'm going to waste a bit by slacking on this and pulling it down through. Trying to waste as little of this expensive wire as possible, right? But it's literally like we're sewing here sometimes. So I would like to get the resistor to go right up to the sense pin, which it will. What I think I can do, get the battery terminal into place, pull the NTC lead down through here, get it relatively taut. Use that as a pivot point to get this guy down. Want to get this guy around the battery terminal, then up to interface with the current sense resistor. Now soldering to that battery terminal is going to be tricky because this little piece wants to keep coming up. Make sure the battery terminal doesn't move on us. Let's feed that resistor down through the sense pin point. Make sure that lead is straight. Secure it there. We'll do a little twist weave over here. Anything else that has to go to that ground? The 124. Okay, where is that? It's this guy here. This 124, we can pretty much just weave it underneath the NTC lead. Secure the NTC assembly, and this looks good like that. Crop it. And we just have to get this onto the battery terminal, which I have I used up a little bit too much slack. I've got to release it somewhere. There we go. Now this will go around the battery terminal again. All right, three-handed operation. Down with this guy, and let's wet those dries. Now the only other thing is we want to blob that over real well, because that's a mounting point now. That's not just that battery. I'm gonna blob it over to some of the adjacent pads. So that's quite the monstrosity there, but that should have that pretty secure on there. And that is the weaving of an intricate ground bus. I think that's all my ground. Yeah. Now, did I mind? Because we're gonna have a wire cross underneath there. So I forgot to put the little incision there. So what I do, because this is double-sided, is wherever we have intersections, I will remove the pad on that side. So now when a wire passes through there, it can't conduct into the pad. And I went and got one of these hex to drill chuck adapters. And I can stick that in my electric screwdriver real quick. But I just use this as a hand drill, like literally just with my fingers. Twist, 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 like a little spinning top. Really easy for doing quick little holes. Normally I would do it on both sides, but I forgot to do it on this side. You gotta watch out you don't work hard in copper. Most of this stuff is copper, tinned copper. But, you know, heating it up anneals it a bit. I don't think we're working it enough that we need to worry about it. Now, one of my philosophies is perf board, and sometimes you want to make connections that don't depend on the perf board, which is why I do intricate little spins and turns, twisting and weaving. That's going to be a connection, even if there was no solder on it. That little inverter buddy's not going anywhere now. You ever just get Thomas the Tank Engine stuck in your head? I don't quite have the right grade capacitor. This is an audio grade capacitor, 4725. It'll do. It's what I used in testing. It's just kind of silly. That's our main reservoir cap. It's just short enough to fit underneath this. Running ourselves a pathway here. Just kind of gradually, can you even see? The two-dimensional, I don't think does this justice. We're getting close to almost done. Just coming along nicely. Like, I'm not walking you through the whole process because, like, it's just hours and editing would be hell. But we have established some nice buses, if you can see. It's starting to look nice. This is some of my best work. Having proper wired, proper tools, like, makes things so much easier. Just to make this run here easier, I'm going to shave some of these pads. Especially this is a power bus here. Okay, it shouldn't move. It shouldn't make contact with negative right here. I think this last area here is gonna get a little bit messy. We're ready for one of the last battery connections. Pulling off this bus here. Now, hopefully that's fused into that battery terminal. Right nice. And it will support it. I should just be able to solidly plug on a battery now. Now the debate, do I want to permanently affix this 92K resistor, or do I want to make it socketable so that I can change the timing? I'm gonna compromise. I'm not gonna make a socket, but I'm not gonna put it on this side of the board either. This guy basically has to jumper right from here to here. So we have holes on this side. So what I'm gonna do is I'm gonna mount it kind of like this, floating on this side of the board. That way, if I do want to change the timing, I can easily remove it. It's not all integrated. So now on this side, all I have to do is solder the holes, and boom, our timing resistor is in place. Looks a little silly, but that's okay. So after carefully looking this over, I've determined that this is about as far as this guy is going before I do fitting. The only thing left is the LEDs, and I have to set their depth. And I won't be able to do that until I see exactly how it's going to sit in the enclosure. Now, I initially bought this plain gray enclosure for it, but you know, I also have this green box, and I bought this to, you know, build another pedal because I have one of each color, but I don't feel like building another pedal. And I envision this green. I envision this charger as being green. So I'm going to use the green box. The last colored box won't be a pedal, it'll be a charger. So as per the usual rules of engagement, I will tape this all up so it doesn't get horribly stretched while I work on it. Being careful to make these sides able to be flat as possible for squaring purposes. All right, so I guess this sits right about middle. I got an input jack coming in around here. This box is actually a bit longer than we need it to be. So the holes are gonna go here. Mark across. And then kind of wanna line up, get it as center as possible, and mark where those terminals are gonna be. So that's about where our battery hole's gonna be. Trace these lines down further so I can follow them. Now let's get the battery as center on this as possible. Now I want to trace it out. I've never done this before. This is going to be a little bit more experimental because we need a hole in this box we could stick the battery through. Ideally you want a square hole, but I'm not 100% sure the best way to go about this. This is where I am most likely to botch this up. I'm going to try doing that effect where we drill a whole bunch of smaller holes to equate to, like, you know, one bigger hole. That's going to be fun. I'm sure it'll be fine. We just have to make sure we get our holes where they need to be, which is the hardest part. So a bunch of 1/4-inch holes. I don't even know if my bits are true enough to do this correctly. So without further ado, let's take a trip back to the 80s. Wish me luck, buds. Oh, yeah, we knew that was gonna happen eventually. Oi! That was fun. Doesn't look like it completely chowdered it quite yet. Doing a little remapping. I'm gonna take it slow now. Okay, well, that looks like about as much drilling as we're doing. Chowder jagged edges. Isn't that a Pantera song? Okay, so we have a mess to clean up here. It's probably gonna entail a whole lot of filing. Let's give it a try. Fortunately, this hole's big enough. We should be able to use a rather large half-round bastard. Oh, it sounds great. Oh, it's not gonna go in sideways though. We have to go smaller. Well, it didn't turn out that bad under the circumstances. Of course, it's not completely square. There's a bit of a slope on the bottom one. The top one looks good. The next stage of fitting involves once we determined where everything's going. And it's gonna peep through like that. Now I need to put these holes down. It looks like that accurately lined up enough with center. So, and those holes are right in line, these end pads. Now, that resistor there is problematic because I was expecting to be able to put this flat down and then mark where I want those holes to be. I think that's about as good as that's getting. Hopefully we have a bit of wiggle room when we go to put it together, right? Wait, I can't see where I put my marks. There. Ah, slip with the tool, bud. That's exactly what we need. Okay. Ladies and gentlemen, once again, Pressy Boy. Now the plan is we take these flat bolts and they swage into there some way, somehow, with enough torque. I'm not sure what size we need them to be. But before I actually swage them in, let's just check fit. So, will the board pop on? Ugh, almost. Oh yeah. Shizzle. And now will Mr. Battery fit through Mr. Hole and line up? Oh boy. It was a close one, but it goes. It's all lined up. That is good, sir. That is good. Now I have to figure out where these LEDs are gonna go. They're in these general top corner here. Pretty much this second pad right there. So let's just blow a stripe across. Now, because the LEDs are going to be a little extended leg, there's some wiggle room. 632 millimeters, 629 millimeters. It's also a 1/4-inch hole. All right, now the spread this way, right here and right here. Let's stripe those down. So we should have an LED here and an LED here. And thank God I'm a Pressy Boy. Would you just look at the expression on this guy's face? Nice dimples. Now there's one more hole to drill, and that's for the power input. I'm gonna be using one of these good old fashions right here. And how big of a hole do we need for this? About 12.4 millimeter. Oh yeah, it's a 1/2 inch. And that guy's just going like anywhere middle center here. I'm not too particularly fussy about precision measuring this one. Let's get it done. Now we're just gonna go drilling for some turtles here. Oh, Tay. Oh, now with all our hole drills, we get to clean up this mess and prep for assembly. Oh, the best part, we're almost done, buds. Oh, join me. Over the garbage. What a satisfying peel. Oh, it's not the most satisfying peel. Question is, how much does the silver of this hole bother me? We all know how much I like painting. A bit rough on this one edge here. I'm gonna put a piece of tape over top. Very crudely cut the tape out along the hole. Come on, get out of there. Okay, I think we got all the tape out. And I have like this black paint pen here. It's for marking wires, but it should be just good enough to deal with these imperfections. All right, so apparently we gotta let that dry a bit. Let's get the LEDs in here. Should be able to put these guys in place now. We're gonna have a green and an orange. Green is on this side, power. Negative terminal is turned in. Negative terminal is the shorter one with the flat side. And we kind of snap them into place. The yellow is going to be the activity, and it's also negative turned in. Snap that into place. This pupper shouldn't be going anywhere now. Oh, starting to look nice. Let's peel this off. Hope it doesn't. Oh, that's a crappy lipstick job, bud. I think you know it. I've been out all night partying. Sorry. Hopefully, what alcohol takes off. Oh, uh-oh. I think it's affecting the actual paint too. Uh-oh, are we about to make a mess? Okay, just buff it out. Oh, I keep smearing. Paint's not dry yet. That, or I got a little bit of alcohol and it wetted up again. That paint was maybe a bad idea. Ah, I keep touching the edge of the paint and smearing more paint on. I hate paint. Okay, we got it okay now. Now let's see if I can't get these guys swaged into place. Now maybe these holes need to be a little bit bigger, or maybe if we firmly turn it, it will nicely swage in there without breaking anything. Oh, so far so good. Oh, look at that. Nice. I got these weird bolts on Mauser. I was just exploring their hardware and I saw those. I'm like, hey, those look handy, especially when we need to get them into tight places. Flush rivets. This guy goes right about in here. What mil wrench is this again? Oh, yeah, it's 14. Snugger up. Okay, boom. All right, now let's establish some positive and negative here. I'm gonna go through this hole here and bend down over this. We have negative. That should conduct some power. And positive is nearby. Positive is this bus right above it, which you can choose just about any spot to push that wire through. Just wrap that over. Solder that into place. It's nice just connecting raw power. We don't have to worry about signal integrity. All right, now we have to kind of finagle this into place where we need to get the LEDs through their appropriate holes, which is right here on one side and right here on the other side. Come on now. Aha. Let's get that slapped down. Get the nuts in place. These nuts. Oh boy, I'm excited about these nuts. You're gonna notice I only have 2 mount points. It's because that's gonna be load bearing. The rest of this is just these perf boards are very solid, the ones I'm using for this design, so they're fine. I gotta pull the NTC forward. The theory now. Does everything line up? Oh. It's not quite straight, but that's the nature of the connector that I bought. It goes on one side deeper than the other. So those LEDs should be good right there. Now we can set their contacts into place. Not gonna go too fancy. It'll be easy to remove them if I have to take this apart again, because it's gonna be difficult to get this apart with those LEDs snapped into place. So we just have a couple straight lines and we tack them on. We can tack them off if we have to. Tack, 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 tack. Secure the resistor holes. Crop the excess resistor lead, and we'll leave just a little bit of slack on the LEDs themselves. Now I just need to get power to this thing. Center positive. Get that on there. And which one's the mag negative terminal again? It's the downest, morest one. What is wrong with my language all of a sudden? Another long day, eh? Okay, I got that through that hole. Oh, it frayed. Come on, man. It shouldn't be this hard. That was the last connection. So now I just grab any old decent quality switch and AC power supply, 12 volts, 1.5 amps, more than we need. Well more than we need. Center positive. We're center positive. And that should... Now if I plug it in, is anything gonna melt? No, but we got the light. So we got the polarity of that LED correct. That's a good start. Except the real question is... Ooh! Charging! Booyah! We might have to do one last important test just to make sure. We need to kill some batteries, yes sir? So what is the voltage of this one? 9.4, that's recently charged. 9.0, this one's taken some damage. Oh. Here's a little long-term experiment I've been working on. Bonus points if you can guess what it does just by looking at it. But this thing's been plugged in for like 3 days now. Let's see how it's ran down the battery. 8.9, this is our best candidate right here. We're gonna bust out Monsieur amp meter, set it to milliamps. We'll try to clippy clip on positive here, clippy clip on negative here, then clippy clip and clippy clip. Ha! That, yeah. Those are the numbers we're expecting. This thing is correctly charging this guy. So now it's just like, pop. I think we're done here. The only thing left to do that I don't get to do on my pedals because I screw with them too much. We can put the back cover on now. And there it is, sir. A 9-volt battery charger. That's it. Just a 9-volt battery charger. Because I needed a 9-volt battery charger. And I don't regret buying these 9 volts because I've been using them for all sorts of breadboard experiments. And now I can charge on these guys. And this guy is not fully depleted. So, and theoretically, that NTC's right there. I did test them. They don't have to be touching the battery in order to get readings off of them. And it doesn't matter what the temperature is. All it's looking for is a temperature change. It should be able to accurately get that. So, seeing as this is how not a fully depleted battery, I guess we're gonna see if it does a full charge cycle, full time, or if it's gonna stop before that. I'll be watching, but will you? Stay tuned. I hope you enjoyed this. I like to build stuff sometimes. Battery chargers? No, but I've been perfing up some experiments, bud, and you know, I'm gonna be building on those. So stay tuned. Okay, bud. Okay. Settle down.